Morning and Jai Swaminarayan to all, my dear students. So, in our previous lectures, we learned about the basic overview of signal systems and signal processing. So, in our signal overview of signal, so in that topic, we defined the signal. What is signal? Types of signal, how they are classified, how they can extracted, how the signal can be generated from the various transducers, various circuitries, etc. Then we learn about the signal processing. Why signal processing is needed? As we know, there are more than one signals are there, so we need to separate that signal from each of them. So each signal have their own importance. We know in our power line communication, we heard about that power line communication. So our voice information is transmitted through power line. At that time, we know in the power line 50 hertz frequency is there and our voice frequency is there. So we need to separate our voice signal from the power signal. So two frequencies are there. Among of them, our important frequency is voice frequency. So we are extract the information frequency or sound frequency from that power line. So that is called a signal processing. In our communication channel, we know noise is always additive. So to extract the information signal from a noisy signal, that is also one kind of signal processing is there. We know what the meaning of signal processing. Then overview of system means which type of system is there, for which type of signal is deals with that. Two types of, generally we bifurcate the system in two major domain: analog system and digital systems. Those systems who deals with the analog signal is called an analog system, and those systems who deals with the digital signals are called a digital systems. So, and then why digital signal processing? What are the advantages of digital system and digital signal processing? That also we just studied in our previous lecture. So now today we are just going to learn about the classification of signals. So generally signal can be classified on their nature and characteristics in time domain. So while we learn about the signal, we know the signals are having a various domain representation. Among of them, two major representation of any signal is time domain and frequency domain. So we know from the time domain, signal can be classified, right? How a signal can be classified? So mainly signals are classified in two types. One, continuous time signal, and second one is discrete time signals. We know continuous time signals from its definition, it's an analog signal, and discrete time domain, it is in digital signal. So now we know two types of signals are there: continuous in time and discrete in time. So continuous signal is a mathematically continuous function and is defined continuous in time. So continuous time signal having their own expression. All the signals and systems can be characterized by a mathematical function. As we already know, we need to process, we must have two interaction. We know the convolution theorem, right? So convolution gives us a system response. To find out the response, each and every signal and system function can be mathematically representable then, and then we can process on that digitally. Now discrete time is specified only at certain time instants. We know discrete time means a continuous signal is there. So we are not taking the whole signal as an our information, but we are taking samples at certain time instant. So that means certain time instant means we are taking, suppose a continuous signal is there. So instead of taking the whole information of about signal, we save the information of signal at certain instant time. So that time is called a sample, and the time between two sample is called a sampling time. So this is the basic for signal representation in continuous domain and discrete domain. So continuous time signal, as from the definition, its amplitude is continuously varied and we need to process all time. While in discrete time signal, as we know from the definition, the discrete time signal, we are taking a samples at a time instant, and that is called a sampling time, and that frequency is called a sampling frequency. So instead of taking the all values between two samples, we are taking at values of our signal at certain time instant. Now we know, as per the time domain, signals are classified into two ways. One is continuous in time and second one is discrete in time. Now for the bifurcation is there. Both the continuous time and discrete time signals are further classified as deterministic and non-deterministic signal. So from its definition we know, we can predict the dictionary meaning of deterministic means we can predict what will be the value at what will be the input. For a particular input we can predict what will be the output. So that is called a deterministic, and non-deterministic means a random signal. We can't predict what will be the value for what input instant. Second one is periodic and aperiodic. Periodic means it is repeated at certain time interval, while aperiodic means the repetition of interval time is not fixed. Signal is repeated but repeated time period is not defined. Then next one is even and odd signal. We already know even and odd signal. Energy and power signals, that also we already defined. Now deterministic signals. So if we just talk about the deterministic signal, the deterministic signals are functions that are completely specified in time. Nature and amplitude of such signals at any time can be predicted. The pattern of signal is regular. And can be characterized mathematically. So then and then, if the signal can be mathematically characterized, then and then we can predict, we can find out the particular value of our output for the particular input of our parameter or variables. Let me take an example for the deterministic signal. Let x of t is equal to alpha t. It's a simple ramp function is there. So for the ramp function, the constant value defined by ramp. So here alpha is a constant and that defines the ramp. So at any instant value of t, we can predict the value of x of t. That means if we know the value of t, we can easily predict the value of x of t. So that's why this type of function is called a deterministic signal. Another example of deterministic signal is that x of t is equal to a sin omega t. We know there is a is fixed, omega is fixed, omega is angular frequency, that is equal to 2 pi f. So any sinusoidal wave have a fixed frequency. So that for particular time instant, what will be the amplitude? So that defines by the sinusoidal omega t. So by putting a value of t, we can predict the value of x of t. So both the continuous signal we can predict. So that's why we can say that this function is also called a deterministic signal. For all the signals, and those signals we cannot predict is called a non-deterministic signal. For example, A typical example of non-deterministic signal is thermal noise in electrical circuit. The behavior of such signal is probabilistic in nature and can be analyzed only stochastically method. Another example which can easily understood, the number of accident in a year. We can't predict how many numbers of accident can be happened, right? So this is called a non-deterministic signal and are called a random signals. Now another type of signal is periodic and aperiodic. Classification of signal is periodic and aperiodic signal. A continuous time signal is said to be periodic if it exhibits a periodicity. Periodicity means the rate of repetition. A signal is repeated after a such interval of time. Let me take an example. If x of t is equal to x of t plus t, so at particular interval of t, our signal x of t is repeated. So that's why this function is called a periodic signal. And what is the rate of period, and after what time the signal is repeated, that is called a t. So t is the period of signal, right? So x of t provides us a value, same value at each t instant. And for a discrete time signal, it is said to be periodic for periodicity if the condition of x of n is equal to x of n plus 0 for all the value of n. So in similar way, likewise, continuous time, discrete time also can be said that it's having a periodic if the same value we will get after at each n0 sample. So n0 is the sampling period measured in unit of numbers of sample spacing, right? In general, expressed as continuous time signal, right? And a signal does not follow above periodicity conditions are called a aperiodic signal. Means signal is not repeated. We will not get any value of previous value after that. So that is called a aperiodic signal. Now these are the basic periodic signals examples: a continuous signal and a discrete signal. In continuous signal, each signal, this is a one all signal is repeated at each twice of t. T0 is our fundamental frequency. So at each t, our signal is repeated. In a discrete domain, once again we know that the value of the sample is repeated after each fourth sample. So n is equal to 4. So after 0, 1, 2, 3, 0, 1, 2, 3, our sample values are repeated. So this is the best example of periodicity. The smallest period with which the signal is periodic is called a fundamental period, and it is corresponding frequency is called a fundamental frequency. This is the basic requirement. Now another types of signal is even and odd signal. So if a signal exhibits a symmetry in time domain is called an even signal. The signal must be identical to its reflection about origin. These are the two basic requirements. For continuous time, simple example is that x of t is equal to x of minus t. We will get both the values are same. For t is equal to 1, t is equal to positive, the same value for t minus is the same. And for the discrete time, x of n is equal to x of minus n. And for the odd signal exhibits antisymmetry. That means x of minus t is equal to x of minus t. Thank you very much.